Okay, so this is the only, so we did not have a quiz on this. Is the only new, this is the only material that will be on the test that we didn't have a quiz problem on. So again, to prepare for the test, quizzes 7 through 11, and then the binary search tree where you're creating a binary search tree and deleting a minimum, and then deleting deleting the node that contains the smallest key, and then deleting a node that actually has 2 children. And if you can do that, I think it's fairly straightforward. Then you should be successful on this quiz. The important thing is that, we know the alphabet, right? So I've got it right here. And so let's just, okay, so let's just start this. So, and then so again, so let's just get started in the binary search tree. And I might not draw the whole thing. I might just look at the solution after a while. Okay, so here you don't draw it. Okay, draw the binary search tree that results from inserting these keys. And you're not going to have to draw a series of trees. It's just one tree. Okay, so it's not like the heaps where we did it one by one. So the G goes first, and that's at the root. And then, okay, where do we put the D? Well, the D is smaller than G. So you put D on the left, and then M is bigger than G. So we put it on the right, and then you've got the B here on the left. And then, because I'm having such a hard time, just B on the right, sorry, the left. Yeah, B is less than G and B is less than D. And then we have H. H is actually less than G. E, F, G, no, sorry. H is greater than G. H is greater than G, but it's less than M, and so forth. So that's actually how you build up this tree. And I'm not going to do, I think it's like 16 or 17. And actually I have a prepared solution right here. Right, and so then, you get this. And if you want to know these numbers, remember what the numbers mean? It's the number of nodes, and it's the size of the tree rooted at a given node. So here, like for 16, the very top tree, the tree rooted at G, right here. Well, if you actually count all those keys, there's 16 of them. Also, just remember, there's no duplicates. So if you see a duplicate, you just skip it. So the first time you put it in, and the second time you skip it. Like, are there 2 B's here? No, I thought there might be. I might have taken the duplicates out beforehand. So okay, so and then how do you? So a good way to count the keys. Let's say if I wanted to know the number of keys in like this. Let's say this tree rooted at M. So I want to know the number of keys here. Well. So I think going bottom up is a good way of doing it. So look here. So the 2 children of M are H and T. Well, the number of keys in the tree rooted at H is 4, and the number of keys rooted at the tree at T is 7. So the number of keys rooted at M. So it's the it's size of H plus size of T plus 1. And that plus 1 is to count for the M itself. So it's 4 plus 7 plus 1, you get 12. So I think it's a good way of doing it, just going bottom up. So like the leaf nodes are the nodes that don't have any children. So like W, it's 1, and Y, it's 2. Like U, it's clearly 1. And then for this V, again, it's small, so it's easy to count. But for V, it's 1 plus 2 plus 1, you get 4. I think when you start getting up, even when it starts getting in the teens, I think it's easy to miss. Most students get it right, but I see a lot of students getting the wrong answer off maybe by 1 or 2. So if you go bottom up, I think that's a good way to do it. So for G, well, it's the size of D, which is 3, plus the size of M, which is 12. You add them together, you get 15, and you add 1, you get 16. So any questions on that? How to draw a tree and how to compute the size. And you know what these numbers mean. Like D is 3 because then the number of keys in the tree rooted at D is 3. So that's something you'll probably have to do. Now, what I did in the next part is I said, okay, let's delete the minimum. We're going to delete the node that contains the minimum. Remember, and we're going in ascending order, right? So A is the smallest and Z is the largest. Okay, so to get to the smallest, you start at the root. You start at the absolute root and you just go all the way to the left so you can't go anymore. And B is the small. If there was something smaller than B, it would be to the left of B, right? There's nothing smaller than B. Everything is greater than B. B is the absolute smallest key in that tree. And so when you delete min, we're going to get rid of the node containing B. So the great thing about getting rid of the node containing B is that it doesn't have a left child. It has a right child, but it doesn't have a left child. So what do we do with C? So when you eliminate B, let's say, okay, I want to eliminate this B here. Okay, what happens to C? Well, C will just become the left child of D, right? So you delete the min, the right child, the node that you deleted, the right child replaces the node that you deleted. Okay, and we can do that because B does not have two. If B had two children, then that would be a problem, like, because now you have to do something with the right and the left. But when you delete the min, all we care about what's going to happen to that right child. So when you delete the min, see, it looks something like this, right? D is now we just moved that C up to where B was. Okay. And then I said, so, and you don't have, so I said, for the second case is that don't redraw n, because you've done it once. You don't have to show me again. Any questions on how to delete the minimum? And then the only other thing that we have to do as far as right now for binary search trees, there's going to be more after the test, is now what happens if, so you have this key M here. See, this has two children. Look at T. T has two children. They both have two children. Let's say I want to delete M, or I want to delete T. Well, if I delete M, okay, it's got an H. You know, I could say, okay, well, let's just replace wherever M was. Let's just put H in its place. Well, okay, but then what do you do here? Because what happens to T? When, or if you replace T with if T takes the place of M, what's going to happen to H? Because T already has a, if we just say, okay, let's take M and replace it with T, well, T already has a left child, so what's going to happen to H? The same thing with H. If we replace M with H, what's going to happen to T? Because H already has a right child. So yeah, it's a dilemma, but is it a dilemma? No, it's not. Remember, we're going to replace with the successor of the key. And the successor of a key is the smallest key on the right subtree, in the right subtree. So for M, here, let me use a different color. Here's the right subtree of M. So for M, you want to find the smallest key in that right subtree, right? So you go one. So to get to the root of the right subtree, you start at M, you go one to the right. Now you're at the root of the right subtree of M. And remember, how do you find the minimum value in a tree? You start at the root and you go all the way to the left. So if I want to find the successor of M, again, that's the smallest key in the right subtree of M. You go one to the right and all the way to the left, and it's R. So the successor of M is R. Right? Let me write that R just a little bit better. Okay, so the thing we know about R, look, it's the smallest key on this right subtree. So all these other keys like S and T, V, U, Y, W, they're all greater than R. So if I replace M with R, well, everything to the right of R will be greater than R. So it won't violate this binary search tree property. And the one thing I know about R is that it's bigger than everything on the left subtree of M, right? Because everything on the right is automatically greater than everything on the left. So we'll replace M with its successor. Let's say if you replace M with anything else, let's say you replace M with S, well, that wouldn't work because R is less than S, right? So if you replace M with any of these other keys, R is going to be on the wrong side. So, but we're safe when you replace the successor with, if we're going to delete M, replace it with a successor. So, and remember, when you delete a minimum, when you delete the minimum, what's going to happen? What's going to happen to this right subchild Yeah, the right child of R. Well, it's going to become the left child of T, right? So you delete R, right? So when you delete R, S becomes the left child of T, and then you just replace M with R. Do I have an answer here? Yes. So we're going to delete M and we replace it with its successor, right? And so now see the R, basically what happened is, let me scroll up just a tad. This goes away, the R goes here, and now S becomes the left subchild. And here's what, and it's kind of drawn a little bit nicer here, right? S is the right subchild, S is the left subchild of T, and wherever you saw M before, you now see R. So R was moved up from here, R was moved up from the right subtree to, all the way to the where M used to be. And we've deleted M. And the great thing is, look, everything to the right is less than, everything to the right is less than R, and everything on in the left subtree of R is less than R. So we still have a binary search tree. So just remember, when you make these, do these substitutions or whatever, you still want to have a binary subtree at the end. So sometimes students, they kind of make stuff up. They give me something, maybe even it's still a binary search tree, but what I say to them, if you can write the code that does it, I'll give you credit. Because there actually is code that does this. It's the code that does this deleting, deleting R or deleting M, it's kind of the code's difficult. So, all right. So any questions on that? Okay, so just assume there'll be it's very likely there'll be something like problems 1, 2, and 3. And now I'll talk about, now I'll talk about, what do I want to talk about? 2, 3 trees. Yeah, I'm so excited about talking about binary search tree. I can't think. Okay, so now this binary, this 2, 3 tree will not be on our test. It'll definitely be on the final, and you'll have a quiz on it. And the whole idea, look at this tree here, and you notice it's kind of lopsided. Like, yeah, this tree. Let's go back here. Yeah, I guess I got scratch marks all over the place. But if you look at this tree here, it's kind of lopsided. Like, let's say I want to go from G to C, you have to go through 2 links. You have to go, G to D and D to C. Okay, but let's say you want to go, let's say from G to W, where you go, how many links? It's not really a lot, but it's 1, 2, 3, 4, 5. So to go from G to W, go through 5 links. To go from G to C, it's just 2 links. So it's a little lopsided. And so our goal is to try to keep these trees as balanced as possible. And what we don't want, what we absolutely don't want, are these long trees. We don't want a tree that looks like A, B, C. This is bad. We don't want this kind of long tree, because then it's just like an array, right? The whole point is that we're doing searching. We're searching through this binary search tree. And if we find the key, we extract the associated value. And the one thing about an array, we start at 0. Oh, is this what we want? No. Okay, go to 1. Oh, is this what we want? Potentially, you can look at, it's order n. You can, maybe what you're looking for is not way to the end, or maybe it doesn't exist at all. So you might end up doing n comparisons. So our goal for the binary search tree is, let's keep the number of comparisons to like a multiple of log of n, which is a lot smaller. So like, if we're talking about log base 2, like log base 2 of like of a million is about 20. Right, so 20 versus a million. Okay, so that's significant. Okay, so especially if you're doing it over and over and over and over again. Okay, so let's just look at the notes here. So this is the 2, 3 trees attempt to do. Okay, here, so, and I wrote these notes this morning. So normally, so I've never done this online, just totally online before. Well, I've never taught this course. Everything I've done is the first time, because I've never done this online before. And I didn't do this. I've taught, well, actually, I have taught this course online. I shouldn't say that. I taught it in the middle of last spring. We went on break. That's when we kind of started going online. And then last semester, I just never taught this 2, 3 tree stuff online. Okay, so we're going to learn how to create use the 2, 3 tree algorithm to create a balanced tree. And it's a virtual tree, meaning there's no actual code behind it. But it's going to motivate us for what's called left-leaning red-black binary search trees, which is, I think, kind of a fun topic. And we're going to see how we can keep our trees balanced. So let's just look at a few definitions. So Well, the root of a tree, I think some of this we know already. The root of a tree, it's the only node without a parent, right? Right. And leaf nodes, so the nodes in a tree without children nodes, right? The left child is null and the right child is null. The height of a tree, that's the third one here. So that's the maximum number of links that must be traversed to go from the root to a leaf node. So you consider all the leaf nodes and what's the longest distance from the from the root. Okay, the distance of a node, so it's the number of links that must be traversed to go from the root to a node. And then a balanced tree is it's a tree where the distance from any leaf node to the root is identical. Okay, so let's just take a look here. So let's just look at this example here. So here, like the first one, the height is 4, right? Because to go from H to A, right, requires, 1, 2, 3, 4 links, right? So if I want to go, so we consider the maximum distance of a leaf from the distance is the maximum distance of a leaf node from the root. So again, this isn't so bad because it's so small. But look at 2. 2 is perfectly balanced, right? To go from R, to any of these A, Q, W, Z is exactly 2 links. So this is our goal is something like 2, right? Because then the searches are like log of n, right? The first level has 0, level 1 has 2, this third, like this level here has 4. So to go from R to a leaf node would take about log base 2 comparisons, versus if it's just like a long, everything is just one long line, then it's order n, which maybe is kind of used. So I got a little distracted by this text message on my phone. I get all these alerts because why, I don't know why. Maybe my life isn't exciting enough, so I get these alerts. Okay, so anyway, so 2-3 trees, just some algorithm for creating a balanced tree. We don't have code for a 2-3 tree. I think we could write it. I think maybe that's an exercise in the Sedgwick textbook. We use it for motivation for the left-leaning red-black binary search trees, which will be discussed a week from today. Okay, so every node in a 2-3 tree will either contain 1 key or 2 keys. So this is what's different. So that in a 2-3 tree, we can have a node with 2 keys. In fact, even 3 keys at a time, but that doesn't last. Okay, so a node with 2 keys, well, just write it so that the smaller key is on the left, right? So when you write the keys, just don't put it arbitrarily. So like you would have BQ instead of QB. So the smaller key is on the left. It'll really make life a lot easier for us. Okay, so a node with 1 key has 2 child links, a left and a right. That's what we've seen. That's what the binary search key has, a left and a right, or a heap has a left or right. But a node with 2 keys will have 3 child links, left, middle, and right. And then we also got these temporary nodes with 3 keys that have 4 child links. Okay, we'll see what happens with those in a minute. Okay, so let's just look at this description here. Okay, so the first key inserted into a 2-3 tree is placed at the root. And so the root's a leaf node. So let's say you just have a tree with just 1 value in it. So like, oh yeah, so the message is coming again in case I didn't get it the first time. Okay, so anyway, so let's say you just have this, let's not use. So let's say we have, let's say the first key is F, and we insert in the tree. So F is at the root, and it turns out the root in case is also a leaf node, right? Because the right child and the left child are null. Okay, so the root is also a leaf node. So here's the big thing about 2-3 trees. Except for the first key, every other key is inserted into a leaf node. So we always insert all the other keys into a leaf node, and if we end up with a node with 3 keys, we do what's called splitting the node. And that's what's going to keep it balanced. Okay, so and that's what I say. If a key is placed into a node that already has 2 keys, then the node is split by moving the middle key up a level. Okay. So let's just look at a simple example here. Okay, so we put A into the tree, so A is all by itself. Right, so the first key you put in, you put it. That's the only time that a key will be all by itself. Okay, every other key will be put into a node with at least one key in it. So now we're going to put the R in. Well, you put it right with the A. R is greater than A, so you put it to the right of A. And now we put the B in. And also, so notice that, okay, so also with AR, that's a node with two keys in it. So now we have the three links, the left, middle, and right. So anything that middle link would point to keys that are between A and R. Like left, well, there's nothing less than A, but the left link would point to keys less than A, which is, they don't exist. And the right key would point to keys greater than R. And the middle one is for keys in between A and R. Okay, so now step 3, we put the B in. Now, oh, look at this. We have a node with 3 keys in it, A, B, and R. So when you get that situation, it doesn't last long. You just kind of, you do what's called splitting the node. And that B, the middle key, moves up a level. So all of a sudden, this tree, which had height 0, right, because it was just a node, now has height 1. And that's how you add to the height. But also notice that it's perfectly balanced. And so every 2-3 tree, if it just has 3 nodes, we'll have this shape right here. This is upside down V. And then the keys, of course, go in ascending order, A, R, B, okay. It doesn't matter really which order you enter them. The shape will always be an upside down V. There's just 3 keys. Okay, so let's look at, okay, but this is an example of splitting the node. Okay, so the left child of B is A, the right child of B is R. So now, students, so just have a couple more examples. And this is what I would do in a class. And I think I'm not even sure I had notes then. I think I would just do some examples at the board. And then I give out a worksheet, we do it in class. Usually most students caught on to this. Okay, but we're not in the classroom. Maybe next semester, I think. So there'll probably be a different teacher than me. Okay, so insert CSHDRAZ. Okay, so the first time we put the C in, so I'm going to circle it if there's more than one key. Otherwise, I don't think I circled it. Okay, we put the C in. The C is at the root. It's the only time we insert a key in the node and it has one key. Then you put the S in, and now, right, you have this what's called some books call it a 3 key. No, yeah, just the 3 stands for the number of links, but you have a node with 2 keys, and there's right, middle, left, middle, right. Okay, then we put the H in, and as we learned, we split it. So yeah, so when you put a key in, so that's the shape of any 2-3 tree with exactly 3 keys. It's always going to be this upside down V. Okay, so let's put the D in. Okay, so where would the D go? Okay, well, the D is left of H, right? D is less than H. Oh, so you get to this. So now you get to this leaf node that contains C. Just put the D there. Okay, so then now let's do the R. R is greater than H. Right? R is greater than H. So we join it. So we go to the right of R. Oh, there's an S. We join R and S. Okay, and I think the example continues. Oh, we still have A and Z. Okay, so again, notice that this is perfectly balanced. And now you add the A, right? Is that what I said? We add A? Yeah, we add A. Okay, so when you add A is less than H. So you go to the right. So the leaf node where we add A is CD. So you have ACD. Uh-oh. Well, you remember what we said? We were splitting the node. The middle one goes up a level, so that C joins the H. That C will join with the node containing H. So now again, it's still a perfectly balanced tree. And we've got how many nodes in there? We got 6 keys. Okay, so then students, there's one more. Is it Z? Is that the last one we're adding? Yeah, so now we're going to add Z. Okay, Z is to the right of H. Yeah, so Z is greater than H, so we go to the right of H, and we join Z with R as Z. Oh, but look, that's a 3 node. So we have to split it, and we put, again, make sure when we write the keys that we add a key to a node, that the keys are in alphabetical order, in ascending alphabetical order, and you have R, S, Z, and the S moves up a level. And then you have A, D, R, Z are the leaf nodes. And then, but look what's happened. The root, CHS, has 3 keys in it. We have to split the node again, and the H becomes the root. And that's it. And it's a perfectly balanced tree. So any questions before we look at another example? And so you'll do something like this for me, not tomorrow, but next week sometime. Okay, so okay, let's just do one example, and then I think I'll start this, and then we'll look at the solution. Oh, easy question. It's one of my favorite ones. Easy, well, there's the second E was taken out. Just remember, students, if I had put the second E in there, we would have ignored the second E, right? Because we know we don't have duplicates. So why don't I start this? Yeah, so, and then we're going to do all the same stuff for red-black binary search tree, but that's not till next Monday. Okay, so this isn't too bad when the number of keys is small. So let me just do about a few of these, and then we'll just look at the solution. Okay, so let's actually, so how many keys do we have? We have 6, 10. Okay, so it'd actually be 6 steps, but we're not going to do 10 steps. We're not going to do all of them. So E all by itself, that's 1. And then 2, A, E, well, that's not so bad. And then 3, A, E, S. And then you split the tree. Okay, so again, so when you just have 3 keys in it, it's always that upside down V. And it's always in ascending order, A, E, S. As you go from left to right, and then 4. Now we're going to add the Y. Right, we're going to add the Y. Y is greater than E, so we go to the right, and so we join the Y with S. And again, it's always perfectly balanced. So if your solution is not perfectly balanced, if at any point the tree becomes not perfectly balanced, and you know you made an error. So remember, perfectly balanced means the number of links you must go through from the root to any leaf node is identical. And so in this case, it's just 1. To go from E to A is 1. To go from E to SY is 1. Okay, so that's what I mean by perfectly balanced. And so then now we're going to add the Q. Well, the Q is greater than E. So, okay, so we add with that node SY. So it's E. A is all by itself out here. And then it's Q, S, Y. And we're going to move the middle key up, right? So it's a 3 note. You've got 3 keys in there. So that can't stay around forever. We move the middle one up. So make sure you write it in the correct order, else you'll move the wrong key up. You get E, S. And then A is to the left of E. And then Q is in between E and S. And then Y is greater than S. Okay, so then should we do one more? We've done 5. Let's do Q. Well, let's just do one more. We'll look at the solution. Like, let's say you do U. U is easy because U is greater than S. It'll just join Y. And then T, maybe this is where I stopped in another class. Let's just do T, and then we'll look at this complete solution. So 7, so you put the T, well, T is greater than S, so it goes to the right, E, S, A, Q, and write it in order, T, U, V. It is the right one, right? So I think so, yeah. And then now you split the node, right? You got 3 here, so the U joins, so it's E, S, U. A is to the left of E, and then Q is in between E and S, and then T is in between, T is in between S and U, and then V is greater than U. V is greater than U, but we've got a 4 node. We got these, we've got 3 keys in one node, so we can't have that. So we split it again. The middle one goes up. So it's S, E, U, and then A and Q. The 2 left links go with E, and the 2 right links go with U. And now that's, again, now we're done. We're done actually inserting that last key. And then, so yeah, so we get, yeah, it's perfectly balanced. Okay, so let's just look at let's finish this up here. So what did we just added, the 7th key we just added was, we just added the T. Let's look at the ION. Sometimes I've made mistakes on this. So let's see here. So, okay, so this is not, okay, hello. So we added the T. Oh, yeah, so we added the T. So now, yeah, so we added the T and we got to this step right here. Okay, so now we add the I, right? We added the T, so now we actually have to, now we still have to add I, O, and N. So okay, I is less than S, I is greater than E, so you get to the Q, right? I is less than S, greater than E, you get to the Q. So you join I with Q. Okay, so that's fine. This is where, it's just the end where I've seen a lot of students make errors. And then the next one is O. Well, O is less than S, O is greater than E. Okay, so what's gonna happen is O is gonna have to join here. It's gonna be IOQ. And you're gonna have to split the node. Yeah, so you get IOQ, and then you split the node by moving the middle one up, right? So you get AIQ, and that's fine. So it's perfectly balanced. And the last one is N, and N is less than S. N is in between NO, isn't? I think this is where a lot of people would make a mistake. N is in between E and O. So N should join that middle one. I think it should be IN. N is. So we actually, so when you put the N is less than S, N is in between E and O, so it joins that I there. So students, yeah, Marcos and Jose, that's all it is. And I think the thing is you just have to try it yourself. But I think this will get you started. And then next Monday, what I'll do is I'll do another example of this, and then we'll do left-leaning red-black binary search trees. And the whole idea behind the left-leaning red-black binary search trees that we're going to go back to the regular binary search trees where there's 1 key per node. But like those nodes with 2 keys in them, all the nodes, all the links will be colored. Have some kind of color scheme, and so it's or color coded. And so you'll either have red links or black links. So all these links in the 2-3 tree correspond to black links in the red-black binary search tree. And then these nodes, like the ones that are circled, the nodes with 2 keys, they're actually joined by a red link. So like, and the bigger one is always the parent of the smaller one. So like here, what we have is S. This is coming attraction, right? Yeah, you have S. Let's not, can I pick something out? This, yes, I hope that's right. Okay, so you have S. I think that's correct. Oh, it doesn't matter. Okay, so you have S, O, and I'm not going to do the whole thing. So S points to O, and O would point to E. I think I got orange there. But now this would be a red link, E. Okay, so all these links that are, all those red links really are kind of correspond to those, and then A would be a black link out of E. Okay, so we would actually go from 10 to something like that. Well, we draw the whole tree, but all those nodes with 2 keys in them, that's actually what the tree looks like. Okay, but the thing is that every other link will be red. So the height of the 2, 3 tree is log of n. So at most you're doubling the number of nodes. So the height of a 2, 3 tree is like 2 times log of n. So it's kind of a clever algorithm to keep a tree balanced. So next time we're going to learn how we can actually start from scratch and create what's called a left leaning. See, left leaning, the red links lean to the left. A left leaning red-black binary search tree. Some books will allow the red links to go in either direction, but I'm just following Sedgwick, and he always has it going to the left. And to be honest, I think it's a lot easier to have it just go in one direction instead of both. So anyway, so that's so again, it's coming attractions, but any questions on binary search trees in general?